Thank you very much, Fiona, for those introductory words. I'm happy to be here with my co-chair, Rachel, and looking forward to some really great talks. So our first one is by Hamish Robertson, coming from Bristol. Hamish, if you want to share your screen, we can get started with the first talk. Fiona already gave you guys the breakdown, but you'll get a 10-minute warning, and then we will have about 7 minutes for questions. So please, get them written in your chat, but don't send them until afterwards. And with that, Hamish, I will give you the mic.
Hi. Thanks very much. Okay, so today I'm going to talk to you a bit about a new solubility constant for dolomite and the implications for subsurface reactions. Okay. So I'm going to start by discussing a little bit about the thermodynamics and kinetics, a little bit about the methodology we use, the major result that we have, which is that US groundwaters are all at calcite dolomite equilibrium, a new solubility constant dolomite, the one we've generated, and the applicability of it for carbon capture and storage. So just to keep everyone interested, I argue that we need to employ carbonate sedimentologists for CCS projects. So thermodynamics deals with can a reaction proceed, the volumes precipitated, dissolved of minerals, and typically thought better understood than kinetics. Kinetics, how quickly an equilibrium is established, and typically it's poorly constrained. So how we calculate a solubility constant. We all know salt and how it dissolves. The solubility constant equals the products over the reactants, and specifically we're looking at the activities of sodium and chloride ion multiplied. Activities approximate concentration. And so what we do to work out the solubility constant is we do this over a number of temperatures to work out the temperature dependency of the solubility constant, and we fit it to something called a Meyer-Kelly regression. So this is the dolomite solubility constant. This is the calcite solubility constant, and this is really, really well constrained. And the thing I want to draw your attention to is as you merge them together, at simultaneous calcite dolomite equilibrium, we can relate the really well constrained value of the solubility constant of calcite through this ratio, which is the activity of calcium over magnesium, to the dolomite solubility constant, which is what we want to work out. Now, the only other thing we need to know is the equilibrium temperature which this solubility constant is established at. So solubility constant dolomite can be calculated either experimentally or with groundwater. The groundwater approach is more accurate than the experimental approach for various reasons, particularly to do with kinetics. So the methodology we use the USGS produced water data set, and we filter it down to about 11,000. And so we know the chemistry of the samples. We also know the depth from which they came from, but we don't know the temperature. So in order to work out the temperature, we've developed a new geothermal model for the US. So it incorporates surface temperatures, incorporates geothermal gradients, and that's how we work out the temperature at formation depth. And just for reference, we've ground truth both of these in a couple of locations. Sorry, the geothermal model and the geochemical data set. So we take our geochemical data, we take our new at formation depth temperature, and we stick it into Freak using PITSA, and then we calculate the activity of calcium over magnesium. And what we find is that there's a really nice consistent increase in calcium over magnesium with temperature. And this is consistent with a wide variety of other studies that have looked at the activity of calcium over magnesium relationship at calcite dolomite equilibrium. And our interpretation is that over 90% of US waters are at calcite dolomite equilibrium. And more broadly, any subsurface water globally is also at calcite dolomite equilibrium. And this is regardless of the lithology of the aquifer that it's hosted in. So it's not dependent on the ionic strength. This is calcium magnesium. It's only dependent on the temperature dependencies of the calcite and dolomite solubility constant. So yes, not dependent on ionic strength, not dependent on pH, PCO2, or equilibrium with a bunch of other minerals. Our interpretation is that it's dependent only on the composition of the dolomite phase, be it calcium or stoichiometric. So more specifically, we interpret that our sort of best fit line has got a composition of about 51%. Values lower than that are slightly more calcium, and values higher than that are typically going to be more stoichiometric. What we interpret it not to be is to do anything to do with ordering. Now, there is a more broader question about whether disordered dolomite even exists, and our interpretation is no, it needs updating this term. And so onto this sort of point, sort of the historical thermodynamic concept of cation disorder as implemented in thermodynamic databases is incorrect. So our new solubility constant is drastically different to the ordered Dolomite phase, which is also typically in thermodynamic databases, the Dolomite phase. And so all reactive transport models using these phases are significantly in error. So just to show this, our new constants in yellow, the ordered Dolomite phase is in orange, and the disordered Dolomite phase is in red. And this is, and the top is time. This is a 2D reactive transport simulation, identical kinetics for all the Dolomite phases. And we've got seawater, and it goes through this column that is initially 99% calcite with a small amount of Dolomite seed. So we don't have any Dolomite forming at the top, but Dolomite starts to precipitate where the temperature's a bit higher and it's not so kinetically limited anymore. And then we get some Dolomite forming in the bottom with the remaining magnesium in solution. So the key point here is that ordered Dolomite is overestimating the volumes of Dolomite precipitated and underestimating the time to dolomitize. Okay, so statistical processing, how we developed our constant. Most people understand the concept of linear modeling. You have all your data, you stick a line through it, you fit it to a regression. What we use is something called mixed modeling, otherwise known as partial pooling. So each data sample has a sort of categorical attribute. In this case, it's either basin A or basin B. And what happens is that the main regression line is weighted slightly differently, so it moves a little bit and it's slightly more accurate, especially for grouped data like this. But also we generate what are known as random intercepts. So essentially we develop unique local Dolomite constants for each of our two basins in this case. So we actually use 7 different random effects or categorical attributes. So we're looking at the formation, the lithology, the field, the sample depth, and geological time series. So we generate about 20,000 unique Dolomite solubility constants. So we're looking at these random intercepts, and we can use them to correlate Dolomite compositions to facies and digesis, or this is what we're trying to do at least. And this is both spatially and temporally. So the random intercept here is on the y-axis, and I want to draw your attention to the period and the series. These are random intercept values. The sort of the main regression sort of value, the global average, is the dotted line, and you can see it kind of jumps around a bit. So what we're trying to do is understand whether these values are statistically significant. So this is a combination between global sort of effects and sort of local effects, and we're sort of favoring, no, these are not statistically significant. It's more to do with local sort of processes, but there's a bit of a question in there. But what I want to get on, our new constant. So here's the line for ordered Dolomite calcite equilibrium. Here's the line for disordered Dolomite calcite equilibrium. And this is our new constant that goes right through the sort of the middle of them. And as you can see, over the past 40, 50 years, there have been a lot of estimations of the Dolomite constant. And but we find that our one is really consistent with global estimations of Dolomite calcite equilibrium, both in Spain, we're really close to, and Italy, these geothermometric studies, and also in Texas, which is kind of one of these seminal groundwater Dolomite estimations. Okay, so I want to talk a little bit about carbon capture and storage. So in carbon capture and storage, we inject CO2 underground. We dissolve Dolomite and calcite close to the well site. And then more distally, what happens is the carbon dioxide is trapped long-term in Dolomite and calcite. Okay, so what happens is that as you dissolve the Dolomite and the calcite, you actually improve the CO2 trapping potential of the brine phase. As this is to do with what's known as a process called ionic trapping. Okay, so we've been able to calculate injection and sequestration potentials for all of our Dolomite fluids. And because we know what the thermal gradient is, we know what the water chemistry is, we know what the pressure is, or at least we can sort of evaluate what the pressure is if we just assume it's lithostatic. And we've also now got our local Dolomite phases. So what we don't have, though, is any additional mineralogy, such as anhydrite and dorsanite. We're not being able to incorporate that. So we're just really looking at the equilibration between dolomite and calcite. So we perform two-stage sort of simulations. So we've got cold injection of CO2 and then hot egg solution of the CO2 thereafter. So this is sort of referring to some of the simulation, some of the recent work on carbon capture and storage by Tutola and all. And essentially what we've sort of come to the conclusion is that understanding the role of dolomite, particularly the different dolomite phases that you might have, is going to be really, really key to carbon capture and storage systems. And there's going to be a really strong role for carbonate stratigraphers, both in sandstone and carbonate systems, guiding the sort of model setup and strategies of. So it's all to do basically with a balance between generating porosity and permeability near the well site, improving the trapping potential of the brine, and then also improving the trapping potential more sort of distally and sealing the reservoir.
2 minutes.
Okay. So lastly, I just want to show some very initial sort of work that we're doing. Essentially, as I said, that we've calculated these potentials for all these different fluids. And so we have a good idea now for each one of these fluids about their sort of their potential to store CO2 in the brine phase. Also, more importantly, understand what the dissolution is like in terms of near the well site, so understanding the mineral changes that are occurring there. And essentially, because this is a two-stage reaction, we've got the injection and we've got the subsequent sealing, we're sort of evaluating these fluids in terms of their potential for injection and also in terms of their potential for storage. So we argue that this data set of models that we produced, and this is an example for the level and feel in the Permian Basin. So we're sort of saying that this database essentially of simulation results that we produced is a potentially really useful tool for sort of the rapid screening of reservoirs, potentially developing cap rocks, and it's really at a sub-RTM scale that we think it might be more useful. So risking and then sort of developing it further in terms of being able to understand things that an RTM simulation probably wouldn't look at in terms of these variations in local dolomite compositions and changes in the formation fluids that occur on a subfield, subformation sort of scale. So come on to my conclusions. Majority of global groundwaters are at calcite dolomite equilibrium. Calcium over magnesium is only dependent on the dolomite composition. Dolomite order is largely irrelevant. Commonly used models are very wrong. This is our new constant. If you want to use this new model, just ask me or any of the co-authors listed. It's also available as a tough react compatible phase, and this includes for all the RI values. This is the paper where all of this has been written up. It's in review at AGS. And then in terms of carbon capture and storage, this database we produced and all these sort of new solubility constants, really powerful applications for screening, etc., and looking to expand. So anyway, yes, lots of commercial applications. Thank you for your time.
Great. Thank you so much, Hamish, for that great talk. Really got our carbonate chemistry session started off on the right foot. For anybody who has questions, please type them into the chat and send them to everybody as we have mentioned before. We already have one, so I guess mine will have to wait. Our first question is from Philip. He wants to know if you can elaborate on what you mean by disordered dolomite doesn't exist.
Is my video on or not? Maybe not.
No, we cannot.
Okay. Oh, well, you don't need to see me. So I've just realized that I'm not. Okay, so yes, disordered dolomite doesn't exist. Slightly provocative statement, I know. So I thought someone might ask a question. Okay, so ordered dolomite and disordered dolomite, it sort of comes from this whole concept from the Braggs-Williams model of 1936. And I think it's a really important discussion that the carbonate community needs to, sorry, my boss just told me to turn up. Oh, I don't know how to do that, sorry. Yeah. There, right. Okay, so it comes from this discussion of Braggs-Williams. Essentially, the way in which, okay, so ordered okay, so if you have an ordered dolomite and you drive the temperature up, what happens is the temperature reflections, the the sort of the XRD reflections decrease, and it at a point which equals the what's known as the critical temperature, they all disappear. So essentially, that is true disordered dolomite. Now, this whole concept comes from sort of metallurgy and essentially quenching of these high temperature crystal phases, and you then sort of drop the temperature, and you can look at sort of disordered, these sort of high temperature disordered phases. So that was Braggs-Williams. They developed this model in 1936 that deals with disorder and order. And then sort of Helgeson in 78 sort of came up with the sort of the first sort of thermodynamic database, which is then sort of more sort of generally used elsewhere, which had sort of the ordered phase, the disordered phase, and also a naturally ordered dolomite phase. Now, there's problems with this in terms of the thermodynamic databases, essentially. So it's a sort of disconnect between sort of what we find in metallurgy and what we find in sort of, anyway, sorry, it's a very complicated sort of subject. But essentially, my argument is that disordered phase, or the argument is that disordered phases are really only describing a dolomite at 1200 degrees C in terms of the solubility constant. Whereas what we actually find in dolomites is nano precipitates and this other thing called the delta structure. And essentially you find sort of zones of Mg rich calcite amongst very high ordered dolomite. So in terms of the equilibrium ordered phase at the temperatures we're looking at, which is say below 200 degrees C, it's all going to be completely ordered. So I think I should probably move on in terms of time. But if you want to discuss this, maybe we could do it afterwards. It's a really, really important point, and I don't think the community has properly understood it.
Yes, definitely. I think we'll move on to the next question, and hopefully we can get to that in one of the larger discussion sessions. But we want to get to one more. So we have one from Pedro, and he wants to know, what about limestone? Do they have the same influence?
I'm not sure if I quite follow. How about limestone? Do they have the same influence? Perhaps.
I think he means in comparison to dolomite, but Pedro, if you want to add a little bit more information in the chat, you can go ahead.
Okay, so maybe there's a couple of things there in terms of thinking about solubility, high magnesium versus low magnesium calcite. In terms of the influence on sort of like high magnesium calcite versus low magnesium calcite, essentially in terms of the thermodynamics, you don't need to worry quite so much about low magnesium calcite. It's the effect. Okay, so this is our solubility constant in blue here, and then this is what would happen, the orange line, if you assume an ideal model. That's the difference for up to a 4% low magnesium calcite. So it's not particularly massive. Whereas if you add 4% of calcium carbonate into your dolomite, so it's a calcium dolomite of 4%, then the line shifts down quite substantially. So it's all to do, this is assuming an ideal model of mixing, which is probably not true. And yeah, I think that's probably as good as I can describe it. So you don't need to worry quite so much about magnesium calcites, but dolomite, there's a much greater impact on the solubility of dolomite when you add in calcium.
Okay, so we can get to one more question, and Pedro says, quite clear, thanks indeed. We have a last question from Peter. He wants to know if you found much variation in dolomite solubility with the pH of the water. Would this be something that's important to consider when sequestering CO2?
Okay, so in terms of pH, if we go back to, let's go back to our diagram of carbon sequestration. Right, so around here, the actual pH when you inject this CO2 drops to about 4, okay? So it drops way down and you dissolve dolomite and calcite. Now, assuming they're still both there, like assuming you still have dolomite and calcite both still kicking around, you haven't dissolved them completely, the actual activity of magnesium over, calcium over magnesium stays exactly the same. And so this is why it's important to understand the Dolomite solubility constant, because that's what's going to affect your calcium over magnesium ratio. It's nothing to do with the sort of pH and PCO2. So I think I can show this here. So yeah, so this is just an example. Okay, the background electrolyte here is sodium chloride. And this is just, it's going to be the same with pH, it's going to be the same with PCO2. As you increase the PCO2, you dissolve lots of dolomite and calcite, your calcium and your magnesium are going to sort of shoot up essentially, but your sort of the ratio between them, which is, let's say, it is this dotted line, that's the activity of calcium there, and that's the activity of magnesium here. So essentially the ratio between them stays constant. So the whole point is that your concentrations can change, but your activities and the ratio between the activities remains constant because you're buffered by both dolomite and calcite. So that's why it's really, really sort of insensitive to pH, PCO2, ionic strength. It is only determined by the fact of these two solubility constants.
Great, thank you so much for that answer. I know we have more questions coming in the chat, but we're going to have to move on to our next talk. Hamish, thank you very much. If you can unshare your screen.
I'm not very good at Zoom, am I?
I appreciate that.
Great. Well, thank you, everyone. Just to say, there is a lot of great chats and questions coming in on this issue. We're always very exercised by issues of dolomite, and I know this is something that's going to be revisited in the forum, the discussion forum this afternoon, where Nick Tosca in particular is going to be talking about dolomite. So let's go for it this afternoon at that forum. Okay, great. So it gives me great pleasure to introduce the next speaker, Philip Staudigel from Cardiff, who's presenting a provocative title, Recipes for Disaster, How to Cook a Carbonate Climate Record. Over to you, Philip. Philip, you're on mute still.
So I was. This is a project that's sort of grown from my PhD and has since grown a bit through collaborative efforts, most recently with my two co-authors on the abstract who are at the VU in Amsterdam. So today we're going to be talking about chiefly aragonite metastability and the thermal resetting of isotope paleothermometers within them. Then we're going to look at some potential causes for this thermal resetting, different circumstances where it might occur. And then we're going to look at a new proxy that's arisen as a result of this thermal resetting. So just to begin, calcium carbonate comes in two common polymorphs, aragonite and calcite. And these are generally favored at different pressure temperature conditions. So at lower temperatures and higher pressures, you tend to favor the aragonite phase. At higher temperatures and lower pressures, you tend to favor calcite. So when you overlay that stability line onto a metamorphic phase sheet diagram, you'll see that you would really only expect to find aragonite in these low pressure, low temperature, high pressure metamorphic phase sheets. And the literature is quite full of finding that. However, in general, we don't associate aragonite with being a metamorphic mineral. It's far more commonly observed at the surface. And so this is caused by the fact that aragonite or calcite can be the favored chemical precipitate depending on the physical or chemical circumstances in which they form. Here, we see a nice series of experiments that were conducted where they varied the magnesium-calcium ratio and temperature and showed that at these higher temperatures and higher concentrations of magnesium, aragonite tends to be favored. And this is generally attributed to the adsorption of magnesium ions onto the calcite growth phases, which then inhibits the further growth of the mineral, thus allowing aragonite to reach supersaturation. Now, there's also a number of physical processes which can inhibit or favor the precipitation of one mineral over another. Here I have two example papers wherein macromolecules, just organic structures within the calcification space, allow or inhibit the precipitation of calcite or aragonite. And so, yeah. And so if you look at this stability phase, you'll see that thermodynamically at the surface, calcite is the only stable phase. And so if you were to take an aragonite and heat it up to the point where these chemical, where these energetic barriers no longer exist, it will convert to calcite. So here's an experiment that I conducted using sclerosponge aragonite, wherein it was heated at different temperatures. The temperatures are 300 degrees C to 425 degrees C. And you'll see that when you plot the kinetic rates of this conversion process relative to temperature, it follows a nice Arrhenius relationship. And you can use this to predict the conversion rate at other temperatures. So other experiments that are done similar to this, we're looking at clumped isotopes in calcite. And this clumped isotope paleothermometer can be reset through the making and breaking of carbonate bonds, very similar to the process of converting aragonite to calcite. So this raises the question, are these two processes linked in aragonite? Is the mineral transformation also associated with this resetting and making and breaking of bonds, which resets the clumped isotope paleothermometer? Just a quick, just brief interlude about clumped isotopes. It's a measurement of the abundance of the carbon-13 oxygen-18 bond. Specifically, it's looking at the excess of those bonds, where if you form a mineral at a lower temperature, in general, it'll have more of these clumped isotope bonds, whereas if it formed at a higher temperature, it's a more random distribution of bonds. And this is measured as this delta 47 parameter that I've plotted here. This is a series of chemical precipitates that I made during my PhD. And it shows quite nicely that it is a robust paleothermometer. So going back to the main question, are these two processes linked? Well, if we go to this experiment that I conducted, where I heated aragonite to different temperatures and converted it to calcite, and I measured the isotope composition of them. So when we look at the carbon isotope value, you'll see that as the mineral conversion occurs, you incorporate atmospheric CO2. So there's evidence of some CO2 exchange. This makes sense. These were powders that I was heating in atmosphere. So exchange with atmospheric CO2 is expected. You see the same trend in the oxygen isotopes. And when we plot the clumped isotopes, you'll see that I plot the original composition as a circle here, and then the clumped isotope compositions of all of the experimental materials fall well below it. So there's some process that is independent of the mineral transformation that is affecting our clumped isotope distributions. Now, if we look at the oxygen isotope distributions, you'll also see a small change. And so there's this coupled shift in the clumped isotopes and the oxygen isotopes in aragonite when it's heated. And this occurs independently of this mineral transformation. So this tells us that it's probably, at least in the conditions that we're looking at in this experiment, the clumped isotope resetting and the mineral transformation are unrelated to one another. This oxygen isotope shift has been observed in other systems. So here we see sclerochronologies done on a clam that was heated to varying durations at 200 degrees Celsius. And you'll see that the longest heated material is this lowest value, whereas the unheated material are these higher values. Or I guess it was the other way around. But there is this transformation that's observed. Oh, right, because they plotted the delta 18 upside down. So a similar experiment was done for abiogenic aragonite. This was done by Chen et al. 2019. And they showed very little change independent of the mineralogy. And then as you convert aragonite to calcite, that's when you start showing it. So there is no independent shift in Moroccan aragonite, but there is in biogenic aragonite. So this really raises the question of why do biogenic aragonites behave so fundamentally differently? One theory is that because there's this shift in the oxygen isotope distribution, that there's some internal reservoir that they're exchanging with potentially water, which has quite a bit of oxygen. And so to test this, we did an experiment. This was conducted with a PhD student at the VU in Amsterdam. This is Cas Nooit Gedacht, and his various advisors, wherein we took Moroccan aragonite and a bivalve. In this case, it was Tridacna, a giant clam, and we roasted it for 1.5 hours at 175 degrees Celsius. And we measured both the clumped isotopes and the oxygen isotopes of the fluid inclusions within. And what we show is that Moroccan aragonite, as we expected, didn't change at all, not statistically significantly anyway. And the bivalve had a highly significant change in clumped isotopes. And this change is observed also in the carbonate oxygen isotopes, which shifted by not much in the Moroccan aragonite, quite a bit in the Tridacna, and the fluid inclusions, which changed enormously in the case of the bivalve, but not so much in the Moroccan aragonite. And so this tells us that there absolutely is fluid exchange occurring within the biogenic material. And this fluid exchange, despite the fact that both the Moroccan aragonite and the bivalve had the same amount of water, they apparently one is far more willing to exchange than the other. So the Moroccan aragonite just doesn't exchange with that internal water as much. So if water is involved, then we want to know what phase it's in, because it could either be in the form of the just normal fluid inclusions, just trapped water, but it also could have to do with these macromolecules that I was mentioning earlier that are often used in order to promote the formation of one mineral phase or another. We don't know at this stage what the water is associated with, and we're hoping to conduct more experiments to just better chemically fingerprint what's going on in order to reduce just this uncertainty. But it really raises now the question of where could you expect these processes to occur? So one tempting question is, burial. If you're burying your sample, geothermal heating will eventually play a role. And this is shown. There was a number of experiments conducted by Chelsea Pederson.
4 minutes, Philip.
Of course, who showed that that there is this internal reservoir that is the first exchange. So this is clearly something that will occur. Another example that we found is when analyzing shells from archaeological sites. I won't go into the details for time, but we found that archaeological samples were far too hot. And so what we were thinking is if these samples were cooked prior to analysis, then that cooking heating could have facilitated all of these resetting reactions that we've been talking about. And so we conducted a series of cooking experiments where we cooked clams in different ways, and we analyzed the clumped isotope distribution. And what we found is that there is actually a robust relationship between the temperature at which the mineral was cooked and the resulting clumped isotope distribution. And so this then could become potentially a paleo cooking thermometer that's usable by archaeologists. And so just to test this out, we worked with a group of archaeologists in Puerto Rico at the Cabo Rojo excavation site. And we looked at clams from different levels in their excavation. And what we found is that the distribution of clams, of clumped isotope distributions, are generally in line with heating up to about 200 degrees Celsius, which would suggest that these are almejas a la plancha. It's cooked on a grill rather, or over a flame, rather than, say, a soup. And so this is, I suppose this is, I'll just leave it here. If anyone wants to ask questions about things that I might have talked about in the rest of the talk, I'd love that. But I'm going to leave my talk here just in the interest of time. So I would happily take any questions.
Thank you very much indeed, Philip. Great stuff. I'm just going to wait for some questions to come through in the chat. Just one thing that struck me, obviously this potential importance of organic material, trapped organic material in biological carbonate. And we know that the amount and the type of organic material is incredibly variable in carbonate material. Do you have any feeling for this relationship with the amount of trapped organic matter or the type of organic matter? Is that in any way significant?
Yes, in so in these in these aragonites or in any mineral, particularly when it's biogenic phase, there are these macromolecules, and they either are a structural component of the mineral itself or of the material itself. So this could be, you could imagine the protein glue, which binds together nacre, for example, shell nacre, for example, or it can be these intracrystalline materials where it's actually trapped within a single mineral phase, and it's and this is the generally this is how it's understood that these proteins which favor one mineral over another, so these promoter minerals, those generally tend to get incorporated within the individual crystals because they're forming along, they're promoting a particular growth axis, for example. So they come in a number of different varieties, and we don't know at this stage which of them are playing a role. The goal is to analyze materials that have different kinds of proteins, so analyze well-studied materials and study the oxygen isotopes, but we're also looking into experiments that we can do, for instance, bleaching them, which would remove the extra mineral, so the intermineral organics, and then conduct an experiment again. And then if there still is an effect, then we know it's not the external proteins, it's the internal it's the proteins within the mineral.
Yeah, great. Thanks, Philip. So a question from Fiona developing that really on the persistence of these proteins in sediments after deposition. So presumably some of them are a bit more durable through diagenesis potentially than others.
Mm-hmm. We haven't analyzed any non-modern samples for, well, beyond non-Holocene samples for this. So we don't know what the diagenetic potential for these is. It makes sense that they would degrade over time, but we haven't conducted any experiments, and this is very much in the this is very much a preliminary work that we're doing in terms of its burial, in terms of our understanding of how it behaves during burial.
Great. I mean, I know that we do have chitin preserved way back in the Paleozoic. So, you know, there was
chitin's a protein.
Exactly.
Yeah.
So this could well, I mean, but chitin associated obviously with biominerals. So this is exciting. So a question from Pedro. In Paraguay, our limestones are from the Ediacaran period. So do they have any sort of influence in terms of temperature for calcite? So shallow water limestones in Paraguay.
Shallow limestones, if it's Ediacaran, are there major skeletal bioskeletal?
They're there. Yeah, they're definitely there. Yeah.
I would imagine, knowing what I know about the stability of aragonite, I would be extremely doubtful if there's any preservation of primary aragonite from that time.
Yeah, so. No, there isn't, but there is preservation of organic matter. So there is kerogen preserved in the Ediacaran.
Yeah, that makes sense. I would venture to say that the process that I'm looking at occurs within the first very short period of time during burial, and after that, diagenetic exchange, dissolution, reprecipitation is more important than these internal processes.
Thanks, Philip. I've got a feeling that Chelsea wants to ask a question. Am I?
You know, I have a couple of questions. If we have time, then yeah, I'll get to one. Yeah, so Philip, you mentioned, you know, we need to get a better idea of how the initial organic degradation process occurs and where those organics are actually hosted in the aragonitic material. And so what do you think the best way moving forward is for people to look at this? Is it heating to different time frames, same material, looking at then, you know, thin sections? Is it doing elemental analysis? What's your take?
There's a number of different things that, at least if you're asking what I personally want to be doing in the future with this question, there's a number of analyses. For starters, we just need to analyze more materials. The paper that I was showing some results from, the one with Cass, we only analyzed 5 materials. So we just need to study more biogenic material. We should start looking more into biogenic calcites. There's a number of crystallographic factors that I'm interested in. Most notably is I'd really like to look more into crystalline anisotropy, where because of these proteins within the matrix, it actually applies a slight tension onto the crystal structure. And because of that, biogenic aragonite has a shortened C-axis, which crystallographic axis compared to non-biogenic aragonite. And this anisotropy actually anneals during heating, which could be associated with the degradation of these proteins, which then could be associated with the change in oxygen and clumped isotopes in those materials. So I'd like to investigate that relationship more in the future, because that, if true, would give you a solid fingerprint, because then all you need to do is measure the crystalline anisotropy, and then you can get a definitive answer of, has this record been cooked? And that's the holy grail for this, is because if I've come up with this, cryptic diagenetic effect that has will affect the parameters, but in a way that's currently unconstrained. And so having just a tamper evidence seal on your record would be very beneficial.
Absolutely. Unfortunately, I'm getting messages that our time is up for questions. So all of the other questions that are left in the chat will have to wait again for the discussion section. So please hang around and we'll get to all of those. So we will move on to our third talk of the day, or of the session. Tom Kibblewhite, coming from Bristol, is going to talk to us about geochemical modeling of lacustrine sedimentation. And Tom, if you can share your screen, and I look forward to your talk.
Thank you, Chelsea, and morning, everyone. I'm Tom Kibblewhite, a second-year PhD at the University of Bristol. This talk is on the use of geochemical modelling in understanding the processes that control lacustrine mineral sedimentation. I hope to show why geochemical modelling is useful and why we need to consider mineral kinetics. I'll be going through the motivations for this work, describing geochemical modelling in relation to pre-salt carbonates, evidencing the importance of mineral kinetics with results from my modelling, and detailing the future direction of my PhD, notably early diagenesis. A large percentage of all rain falls into endorheic basins, outlined in red. These waters dissolve ions as they flow towards closed lakes, where they evaporate, become increasingly saline, and precipitate minerals. I'll be excluding allergenic and detrital components and focusing on orthogenic precipitates. Saline lakes are very productive environments, hosting many unusual extremophile microbes on Earth and possibly on Mars. They sequester CO2 in carbonates, concentrate metals in evaporitic salts, and as buried paleolakes can form vast hydrocarbon reservoirs that have driven much of the current research into saline lakes. The most well-developed of modern rift basins is the East African rift. It contains hundreds of saline lakes of varying chemistry and morphology. But during the early Cretaceous opening of the South Atlantic, there were rift basins and alkaline lakes unlike anything seen on Earth today, covering millions of square kilometers between Brazil, Angola, and the Congo. These lakes deposited huge thicknesses of evaporite-capped carbonates that now form significant economically significant hydrocarbon reservoirs. This work is designed around the Santos Basin pre-salts, where 4 kilometers of pre-salt carbonates were deposited over 17 million years. The Barravea Formation is the major hydrocarbon reservoir in the Santos Basin, which is highlighted in blue. As it exhibits unusual sediment cyclicity and carbonate morphologies, the geology of the BVF has been assessed by many authors. Last year, J.P. Gomez et al. Classified the sediments based on their mud, shrub, and spherulite components. The shrubs and spherulites are distinct carbonate textures with varying magnesium-calcium stoichiometry. Their origins, either microbial or abiotic, primary or diagenetic, continue to be a point of significant discussion. And the muddy component may be carbonate, clay, or silica rich. Sample characterization like this is commonplace and a vital first step in understanding past environments. JP identifies repeated cycles through his fascies classification and suggests models for how climatic conditions might control this cyclicity. Fewer people are doing this, but as mentioned in yesterday's forum discussion, creating conceptual models from sample analysis is the logical next step. Prior to JP's work, there were other authors that had similarly characterized the cyclicity, and Mercedes Martin et al. Had used geochemical modeling to better understand the BVF. They allow for calcite, magnesium clay, and silica to precipitate under conditions of thermodynamic equilibrium. And they model the effect of varying input and output water ratios. With respect to the BVF, Mercedes Martin are the only ones to have done thermodynamic modeling, which I'll summarize briefly. So here's a graph of saturation ratio and saturation index against time. Saturation ratio and saturation index are measures of how far out of equilibrium a solution is with respect to a given mineral. Water on this dashed line is at equilibrium, and this marker represents the fluid that is out of equilibrium. In order to return to equilibrium, the mineral must be precipitated from the fluid. If, like Mercedes Martin, we assume thermodynamic equilibrium, then there's no time component and precipitation occurs instantaneously. But if this were the case, then we'd never have any waters that were supersaturated. We therefore have to account for mineral kinetics, something that no one's done with respect to the BVF. Kinetic rates. Kinetics limit the rate of mineral precipitation and dissolution. Minerals like calcite have rapid kinetics and precipitate very quickly, whilst dolomite precipitates orders of magnitude more slowly. Most kinetic models use simple kinetics, assuming either that rates are constant independent of water chemistry, or that precipitation rates are equal to dissolution rates. This is because mineral kinetics can only be determined experimentally, and dissolution experiments are easier to run, creating a scarcity of precipitation data. This is an issue because for most minerals, the rate of dissolution is much faster than the rate of precipitation, and dolomite would be a relevant and most well-known example of this case. As this simplification could have significant consequences for predicted mineral assemblage, our model uses separate rates for dissolution and precipitation, which no one seems to be doing in this field. So the model uses Python to automate the running of geochemical modeling software Freak. Each model run includes thousands of time steps that each include 2 stages. In stage A, we consider a 1 litre solution that represents the entire lake volume. We evaporate some of the water, refill it with input waters, allow for any leakage, and equilibrate with atmospheric CO2. This whole stage has no time component and may be unique for every single model step, but in the examples I'll show later, we've kept all of this constant throughout the model. The resulting lake water is then passed to stage B, where mineral reactions occur for the given time step duration and according to the kinetic data. Our model allows for calcite, disordered dolomite, which may not exist, amorphous silica, and sepulite to precipitate. The sepulite is not the most appropriate MG clay to use for the BVF, but it's the only one with sufficient kinetic data, and this data was only published last year, so wouldn't have been possible beforehand. The chemistry from stage B is then passed to stage A of the next time step. This allows for dissolution and affects the mineral saturation and kinetics of the next step. I'll now compare the thermodynamic and kinetic results from my model that otherwise has exactly the same conditions in both models. On the x-axis we have time, and on the y-axis we have ionic strength. Without mineral precipitation, evaporoconcentration increases the ionic strength throughout the model run. If we allow for precipitation, then some of the ions are incorporated into minerals and removed from solution. In the thermodynamic model, we see a linear increase in ionic strength, whereas in the kinetic model, there are clearly at least 2 different sections to the lake water evolution. These trends are reflected in the precipitated mineralogy, Here you've got stacked graphs of cumulative mineral volume, such that if you took a slice through here, then that would represent the total mineral assemblage precipitated up to that point. The initial lake waters in both models are supersaturated with respect to calcite, dolomite, and sepulite. So it's thermodynamically favourable for them to precipitate at time 0. They then continue to precipitate at a constant rate for the duration of the thermodynamic model. In the kinetic model, the onset of precipitation is determined by the kinetics of each mineral, with calcite precipitating within the first few time steps, sepulite kinetics are orders of magnitude slower, and dolomite kinetics are orders of magnitude slower again. For these first 8,000 years, while it's not competing with dolomite, the calcite precipitation rate is much faster in the kinetic model than it is in the thermodynamic model. Dolomite precipitation then removes most of the alkalinity from solution, causing the sepulite to become undersaturated and partially dissolve, which releases more alkalinity and calcium ions back into the solution and fuels further dolomite precipitation. The total precipitate volume in both models is similar, but the calcite to dolomite ratio is shifted towards calcite in the kinetic model. In both models, silica doesn't precipitate because sepulite is using up all of the available silicon. The advantages of this kinetic modelling are best observed as a sediment column. We can clearly see the singular facies of the thermodynamic model, whilst there are at least 4 different facies in the kinetic model. We have the initial calcite layer, a thick 3:1 calcite to sepulite layer that follows an initial spike in sepulite, then transition to wholly dolomitic sediments, and a final transition to sediments that have the same mineral ratio as the thermodynamic model. We're currently exploring the model parameter space. So the previous model runs at 25 degrees C and 400 ppm CO2, but greenhouse conditions during the early Cretaceous mean that it was actually much hotter than it is today. If we increase temperature, we increase dolomite rates, causing more of it to precipitate and for it to do so earlier in the sediment column. If we increase CO2 concentrations, then the precipitation rates of all of the minerals are reduced. We've also begun to explore water chemistry, which is more uncertain than the climate variables, but has a much more significant effect on mineral precipitation. All the examples shown here use water chemistries from the modern day Paraná Basin, because the basalts, the Paraná Etendeka LIP, are the likely source of magnesium to the Santos Basin.
2 minutes.
Whilst these kinetic models improve upon the thermodynamic models, they don't match the observed cyclicity in the Maravilla Formation. This is because we're still exploring the aforementioned climate and water chemistry variables, and because we have not yet counted for diagenetic alteration. Doing this is particularly important as it redistributes the porosity and affects the hydrocarbon permeability in the formation. As COVID restrictions are lifted, field work will be required so that we can validate the results of our modelling. So that brings us back down to the bottom of this sort of model development pyramid. Hopefully we'll be sampling sediments and waters of the best analogue we can find for the pre-salt, though none exist, no perfect analogues exist, considering its size and different climates. Thank you very much for listening.
Thank you, Tom, for that great talk. Everybody, you can start typing your questions now into, oh, we already have one. So you can start typing them into the chat and we will get to them very quickly. All right, your first question, Tom, is from Maria. She wants to know, or says, thank you for the presentation of your ongoing work. She wants to know if you want to comment on the biotic versus abiotic issues. I also had this question.
I'm not sure. I'm not able to comment probably on, I'll just stop and share the, we've sort of not looked into that in this, whether it's abiotic or microbial, but just noted that it's a point of interest and a good reason for studying it. But the model doesn't go anyway towards answering that. But there's suggestions that the shrubs might be primary and may be aided by microbes, and that maybe the spherulites only occur diagenetically afterwards, and yeah, lots of debate about it, which then could affect how you interpret it. And like in the formal discussion yesterday, everything relates to each other and might affect how you go about things, but no, I've not considered specifically in this.
Yeah, I was also definitely curious about how we can maybe start to consider what effect the biological control might have on the kinetics and the resulting models, because of course there seems to be a lot of biology involved in this system. So how that might change something like the rates of precipitation, and then how that might need to be incorporated is definitely something, maybe not your focus, but maybe a follow-up study. Something.
Yeah, our current ones are sort of all based on abiotic experiments and don't yet include specifics of microbial interactions, but definitely something to look into.
Yeah, okay, our next question is from Peter. Is there actually any quantitative evidence that these pre-salt Santos Basin rocks are cyclical? I've run analyses on a few core sections and found no strong evidence for facies or thickness cyclicity, and I've not seen any strong evidence presented by anyone else. So I'm always a little surprised when people refer to these rocks as cyclical.
Oh yeah, again, I've not looked personally into it, sort of basing it on various bits of research, but as from other people's cyclicity, but as I say, ours doesn't yet match that cyclicity, and we're not trying to make it match. We're sort of, all these models use the same conditions throughout for each time step, but we could impose some climatic variation in the input water ratios, and that might induce changes. But we're sort of, we're not trying to replicate this, we're just modeling based on the kinetics and seeing what happens and seeing what conditions would be required to replicate that, whether we actually end up doing so or not.
Maybe again, another question to chat with various people doing research on these basins in the discussion. Okay, so our next chat is from, Rachel. Thank you, Tom. The pre-salt is tectonically active, so the heat flow is very variable throughout time. Can you model that?
So yeah, the model is capable of taking lots of different input waters, which, depending on the size of your time steps, you could have some hydrothermal waters or something coming in at various points. Again, this model has only used the same water throughout just for simplicity, but yeah, if you decided you had some known timeframes where that might happen, or you could model examples of it and have warmer waters coming in and change the temperatures accordingly. But yeah, I've only shown a simple example here.
Might be interesting to have some hydrothermal pulses sort of coming through in your model and just seeing how things would change. Okay, our next question is from Stephen. Thanks, Tom. How did you select the time interval of 10,000 years?
This is sort of the lower end of what JP predicts for his facies cyclicity. So these are sort of, there's not any much dating within the BVF, but the whole BVF formation may have taken some duration and is some depth, which then, based on the cycles that he's picked out, means that somewhere between 10 and 25,000 years is the proposed duration of his cycles. And I just went with the 10,000 one because it's quicker to run models at 10,000 years, but we've also got ones at 25.
Okay, so mainly based on this previous work.
Yeah.
All right, well, you have time for one more question from Ismail. Thanks for the great talk. Congratulations. What causes lake level fluctuations? Any relationship with global sea level or climate change?
So again, we've sort of, in these models there, we've balanced the lake levels. So we evaporate sort of 2% or less off the water and then fill it with some waters and balance it. But the model is capable of being unbalanced. And so yeah, that's something, once we get on to better modeling the climate, is doing that. But we've got
a little bit more in your model.
Yeah. But it's capable of doing all this stuff. And we've thought about it and done some research on how the climate varies, but we're only done as much as other people have already looked into in terms of how the climate changes.
Yeah, perfect. All right, so all of our last questions, sorry we couldn't get to them, but we're going to have to move on to our next speaker. Tom, thank you very much.
Thanks, Tom. Obviously, this is an actively moving area, and I think access to the core is opening up now, so that we should see a lot more, availability to ground truth a lot of these ideas. So thanks very much. So with pleasure, I'm going to introduce the final speaker of this session, Simone Booker from Canada, Dalhousie. And she's going to give us a talk on determining the spatial gradients in carbon isotope signatures of essential amino acids from carbonate sediments. So over to you, Simone.
All right, thank you. So I'm very happy to discuss today the determining spatial gradients of delta 13C signatures of essential amino acids in carbonate sediments. And this is a case study from Grand Cayman. Hold on, my screen is not changing. There we go. So what we want to do is we want to use compound-specific stable isotopic analysis of amino acids to better understand the biological role of, the biological origins of carbonates sediments. So we all know the saying that carbonates are born and not made. So this makes these materials a prime tool for this kind of research. In terms of carbonate sedimentology, understanding and identifying the individual allochems is critical to determining depositional environments. But this can become complicated and hindered as diagenesis increases, potentially rendering microtextural or other chemical tools unusable. But it's been shown that the essential amino acid signatures of carbon isotopes are distinct and different based on the phylogenetic groups of primary producers. So what we can do is use the organic matter trapped within these skeletal components of our carbonate sediments to sort of fingerprint the contributions from the different primary producer groups. This will then enable us to identify the organisms that were living during the deposition of these sediments, and will provide a wealth of information about the depositional environment that may have otherwise been lost to diagenesis. So what exactly is compound-specific isotopic analysis of amino acids? Well, bulk carbon isotopes of organic matter have long been used to understand variability in nutrient sources and food web interactions. But these signatures are often confounded by overlying influences, the variability and difficulty in determining nutrient assimilation rates, and the pathways at the primary producer level. Compound-specific isotopic analysis of amino acids, however, provide a new metric for determining the sources and transformations of organic matter through the ecosystem. This is because the amino acids fractionate differently based on enzyme pathways and isotopic effects associated with their synthesis, which provides us with abundant information about the organic matter movements and metabolic histories within the ecosystem. So we can use the carbon isotopes to identify these phylogenetically distinct primary producer groups contributing to our sediments. But what exactly are amino acids? These are a group of 14 chemical compounds that combine to form proteins. So all organisms contain them and produce them, including carbonate secreting organisms. In carbonate skeletons, they're typically incorporated into the skeletal components in less than 0.1 weight% of organic matter. But it's been shown or suggested that this organic matter can be preserved for 10 to 100 million years. So it gives us a good idea, or that we'll be able to use this in the geologic record. In this presentation, we're specifically interested in the essential amino acids of isoleucine, leucine, phenylalanine, threonine, and valine. And we're interested in these 5 amino acids because they can't be produced by the organisms themselves. They come from their food source and have been shown to be the most readily differentiated between the primary producer groups and bacteria. So they can really help us in fingerprinting these contributions. So what we did for this project is we took 6 bulk sediment samples from various depositional environments around Grand Cayman. And Grand Cayman is located in the Central Caribbean and has a subtropical environment and is characterized by numerous lagoons and fringing reefs that extend from headland to headland. So it's a perfect environment for prolific carbonate production. You can see in my lower map here that there's red dots and black dots. So the red dots are the 6 sediment samples that I'll be talking about in this presentation. And the black dots are samples that we've collected and are either currently in the process of being analyzed or we want to process in the future. So initially we looked at our bulk sediment samples and identified them based on allochem composition. And these consisted of things like corals, bivalves, gastropods, forams, halimeda, worm tubes, red algae, and echinoid spines, of course, abundant micrite and unidentifiable grains. So in order to do this type of research, we first need to isolate the organic matter from the carbonate sediments. To do this, we have to decarbonate our carbonate sediments. This is done by successive baths of 10% hydrochloric acid. And at the end of this, you result with a nice pile of organic material. You then take this organic material and you purify it and process it to produce amino acid derivatives. And this is done using hydrolysis, cation exchange chromatography cleanup, esterification, and then rederivatization. And so at the end of this process, you're left with a liquid that is enriched in amino acids only. And you can take that liquid and then apply it to your GC-IRMS to produce the delta 13C signatures of these different amino acids. Once you have those carbon signatures, you then produce a linear discrimination analysis to differentiate between the different primary producer groups. So what are the results that we got from this research? Well, in panel A, we can see that our Cayman sediment is shown in the red and black symbols, compared against carbonate sediments from various environments in Florida from Carter and Mitter 1978. And you can see that there's very nice consistency and overlap between our data and theirs. Of note is the high percentage of acidic amino acids, which is a characteristic of carbonate biominerals. So that's telling us that we got really good results from our analyses. Additionally, in panel B, when we compared our normalized data to that of Larson et al. 2013, and his data set is based on a huge amount of primary producers, so things like fish, soils, cestins, terrestrial plants, seagrass, fungi, bacteria, different types of algae. You can see that, again, our Cayman data plots nicely with their values. So then we applied our Cayman data to a linear discrimination analysis. And in order to do this, we needed a training data set. And for that, we used the Larson et al. 2013 data. And this produces probability fields of the different primary producer contributions to our Cayman sediment. Our Cayman sediment in the diagram on the right is shown by the black C's. The other letters are the different primary producers or bacteria groups that Larson et al. Have identified. So our Cayman samples showed that 4 out of the 6 samples had greater than 98% probability of being eukaryotic algae, which makes sense when we look back at the allochem composition of our sediment, because these sediments had abundant halimeda plates. One of our samples plotted as 53% probability red algae and 47% probability eukaryotic algae. And again, this is consistent with the sediment composition. And our last sample plotted at 83% probability as seagrass. And this might be a potentially puzzling result, given that seagrass isn't preserved in carbonate sediments. But it's been suggested that as a byproduct of seagrass growth is fine aragonite needles. And these needles can incorporate some of this carbon from the seagrass. And that makes sense given, one, the location that the sample came from on Grand Cayman, which is adjacent to a seagrass meadow, And 2, the abundant mud contributions in this sediment, which would be that fine grain aragonite needles. You'll also notice that we don't have any bacteria or fungi signals from our Cayman sediments. And that's telling us that there's no exogenous carbon to our sediments. So this is very preliminary research, given that we only have the 6 samples right now, but it's giving us ideas of what we can do in the future. So ideally what we'd like to do is to do the same process for a number of individual allochems, which will then allow us to produce a library of sorts for the typical tropical calcifying organisms using these fingerprints. This will then enable us to determine the relative proportions of the different carbon sources, similar to what's being shown in the diagram on the right. So this is from various fish species in the Red Sea, and they were able to identify 4 carbon sources that contribute to the diet of these fish. And we'd like to be able to do a similar thing to that given our carbonate sediments. Additionally, we would like to then apply it further into the geologic record using whole rock analyses. And then, as a fun side note, we want to add delta 15N values, which will give us more parameters to add to our library and better fingerprint these different carbonate producers. So what did we find in this study? Although these are preliminary findings, they give strong support to the potential applicability of using delta 13C of essential amino acids to identify the origins of carbonate materials. This proposed catalog of delta 13C values will provide a critical tool for determining the origins of allochems in altered carbonate sediments and rocks, which you may not be able to do solely on visual identification of the skeletal fragments. Developing an additional tool for allochem identification will greatly advance our ability to accurately determine many aspects related to the development of carbonate accumulations throughout geologic time. Thank you.
Thank you very much, Simone. Exciting stuff. I'm just going to wait for some chat questions to come through. Maybe I could ask you, I'm aware of acidic macromolecules being recovered from microbialite, I think from the Carboniferous, if I remember. Is that about the oldest macromolecules that have been recovered from the carbonate record, or do you know of older examples? Oh, actually, and Jim is asking exactly the same question. How far back into the geological record do you think it can be applied?
I don't know exactly how far. To be honest, when we did these results, we were actually surprised that they worked at all, given that the samples that we collected were collected 5 years ago for a totally unrelated project and kind of just sat on a shelf for those 5 years, instead of being collected and frozen to preserve the organic matter. So like this is the first time I've seen this type of like really degraded material in carbonate sediments being used. But given that people suggested that it can be preserved for 100 millions of years, I think we could probably go back further in time, and it'd be really interesting to look at something that old.
Thank you. Yes, it's just a matter of deciding what target fabric to go for.
Yeah.
Great. Okay, Chelsea. Actually, so Chelsea's asking, did you also run the more standard organic isotopes on the bulk organic material to compare to the amino acid results?
We haven't run like just regular bulk carbon and nitrogen. We have sent them off to do that, but we didn't get the results back yet.
Great. And it will be certainly very interesting to compare this with the nitrogen isotope record, because of course we've got those records way back into the Edinburgh, if not older. So you may be able to make a comparison there.
Yeah, definitely. This is like a very kind of new field. It's commonly been done with like actual living organisms, and there's a little bit of work on siliciclastic sediments, but applying it to carbonates and then into the geological record is like a new area that we really want to explore.
Yeah, super exciting.
Mm-hmm.
Okay, we have a question here from Georgina, I wonder if this method may be useful to better understand the role of microbial processes in, in dolomite precipitation and in ancient Dolomites.
Yeah, if you can get the organic matter out of it in the quantities that are needed for the chemistry component of this, I don't see why it wouldn't be applicable. And it would definitely be very interesting. And it could definitely show you the different microbial influences. The LDA that we used was restricted to just a few of the primary producers. But if you were to build, and people are building bigger libraries for these primary producer groups, you could definitely pinpoint the microbial influences, yeah.
I think the problem is that a lot of, at least Paleozoic and older carbonates, it's just the really, really recalcitrant proteins of the left, like kerogen. However, you could go to some of these really exceptional preserved biotas, like the Upper Triassic sipit boulders that have primary aragonite. And I don't know whether anyone has attempted these more sophisticated organic carbon, organic compound extraction techniques, but there's certainly some really amazing, unusually, almost pristine preserved fabrics that you could target with this.
Yeah, definitely. We're interested in more modern stuff, so things that recently have died. We're looking at actual things that died yesterday as well. But we'd like to build this library and then apply it into the geologic record, because I think that'll show something very interesting patterns.
I had another quick question, just based on how the chat's going right now. I'm curious if anybody's done any sort of experimental work to see the stability of the different types of amino acids and to see when they start to break down. Because of course, if you go further back in the record, like Rachel was saying, you have, of course, the more recalcitrant ones, the ones that are more stable. So how that might sort of skew our view of the organic components in these older sediments that are maybe less well preserved. Do you know of any work that's been done to try and better understand?
I haven't seen anything like that. That would be very interesting though.
I'm thinking even just like simple heating and exposure to different gases, that sort of thing. But I wasn't sure at all. So. Yeah,
given that this was the first time this kind of material has been run, and the fact that we actually resolved amino acids in the first, or organic matters in the first place, was very promising. So definitely we would like to explore. There's a lot to explore for sure.